Hello. She goes, well.
Okay, guys, we'll get started here. So let me take care of the waiting room. We're just about there. Okay, we have a quorum now, so we'll get started. It's good to be back. Still on the recovery trail, but slowly but surely I'm getting back to 100%. So you guys know I'm a big Padres fan, right? They've made the playoffs. Tomorrow they'll play here against the Cardinals. Traditionally, they're thorn in their side. So we're looking for good things for the Pods tomorrow. Thursday and Friday if necessary, right? It's a 2 out of 3. So they'll be battling in their first playoff in 14 years. So it's a big deal for the Pods. Okay, so there were 2 items on the agenda. The first item is our solutions to worksheet 6, which is due tomorrow night. Unfortunately, we couldn't meet last week, and you turned in worksheet 5, and that's in your hopper. I'll be grading those this week. You'll be turning this one in tomorrow night. So let's go over it, and I think we'll have some time left so that we can talk about the solutions to worksheet 5 if you'd like, okay? Okay, so let's get started on this one. Now we are talking about continuous distributions. The coin tossing experiment was a great example of a discrete distribution where the random variable represents basically a count, right? And so in worksheet 5, you saw a couple of discrete distributions. You saw the coin tossing example again. In this worksheet, we're now talking about the continuous distributions, of which there are many, many examples. Daily temperatures, heights, weights, intelligence scores, the lifetime of a light bulb, okay? These are basically measured on a scale, not on the whole numbers. So in contrast to the discrete distributions, now we're talking about the continuous distributions. Those distributions that are basically measured on a scale, like the real line, for example, sometimes the positive real line, right? In the light bulb example, the light bulbs last minutes, hours, whatever the manufacturer has deemed necessary. And, or they could be measured on a negative scale, okay? And sometimes depths of the earthquake is measured in a negative sense, negative 50 meters below the surface, meaning, so these continuous distributions have a range from minus infinity to plus infinity, okay? All right, can somebody give me another example of a continuous distribution? Something that measures something on a scale. Daphne, are you there? Hello, Daphne? Okay. How about Noah? Noah, are you there? Hello, Noah?
Hello? Your weight could be continuous?
Weight. Yes, weight is continuous. Is it a positive random variable, the weight?
Sorry, what was that?
Is it positive or negative or both?
Positive.
It's a positive random variable. Okay. All right. Now, the most useful model in statistics is the distribution known as the normal distribution. There are many variables in applications, scores, test scores, weights, heights. Often these are, the samples can be displayed in a histogram. And if the histogram looks sort of bell-shaped, then we can fit a normal model, estimate the mean and the standard deviation of that distribution, and use it to model the data. So in your readings, you've already seen how that works. Okay. Now in this worksheet, we want to do a little bit of the algebra of normal distributions. Okay. First of all, some notation. Here's our random variable here, x. And x twiddle n mu sigma is a very shorthand notation for describing a variable x which has this bell-shaped symmetric distribution known as the normal distribution. And I have some drawings here that we'll go over that use the normal distribution, okay? And you can see a normal distribution is this very elegant looking bell-shaped distribution, all right? And the key idea is that the area from minus infinity to infinity, or whatever scale the distribution is measured on, has area 1. Remember your relative frequency table? All of the probabilities added up to 1. Same deal here, only instead of a discrete distribution, we have this continuous probability density function, it's called, and the area under that curve is 1. Okay. So let's take the first problem here. And by the way, just another factoid, the axis of symmetry of this bell-shaped distribution is the mean of the distribution. So the mean and the median of these normal distributions is mu. Okay? So these are some factoids that you're becoming familiar with as we adapt these normal distribution models to our sample data so that we can make inferences based on those mathematical models. So that's the whole idea. So in this problem here, we're going to look at a so-called z-score of a realization of variable CAPX. Let's call the variable CAPX. And a sample from CAPX might be lowercase x. And we want to measure the relative distance of x from the mean divided by the standard deviation. Okay. So in this example here, we're told that the variable from which x is drawn, okay, we're drawing the value x equal to 1. It might be a distance. We don't know. We're not told what these measurements are. And we'd like to see, is the 1 value, is that large in terms of the distribution? Okay. So on these curves, you can see that some of these values are far away from the mean, aren't they? The z-score is a handy way to give us a relative distance, and that relative distance is nothing more than the ratio of the difference with the observation x with its mean, there's the denominator, and then we divide out by its standard deviation, sigma. Okay. So when we take that z-score, as it's called, we get a measure of how far above, if it's positive, this value x is above its mean, and or what is the distance to the left of the mean in terms of standard deviations. Is it 1 standard deviation from the mean? Could it be 2, etc.? All right, so let's do our calculation here. Our given value of x is 1. Our mean Remember, this notation tells us that 12 is the mean mu of the distribution, and 3 is the standard deviation. Okay? So mu is the mean, sigma is the standard deviation. Sigma squared is the variance. And I have a typo here, so we're going to have to fix that. Let's calculate the z-score. So 1 minus 12 in the numerator is negative 11. Hold on just a minute. Okay. And now we substitute sigma for 3 and then do the calculation. And we get a z-score of negative 3.666, or in shorthand notation, we put a bar over that 6, okay? So this value of 1, compare it to the mean 12, get a big difference there, negative 11, divide by 3, the standard deviation, and you get this value, negative 3.6, okay? That tells us that it's almost 4 standard deviations to the left of mu. And in the theory of normal distributions, 95% of the data should be within 1 standard deviation. So this one is way out in the tail, the left tail. It's an absolute value, a very large value in relative terms, okay? The mean of this distribution is 12, and the variance of x should be sigma squared, not sigma. Sigma is the standard deviation. I'll correct this and repost it. So that's sigma squared equal to 9. Up here, sigma represents 3, and sigma squared is just 3 squared, or 9. So this should be a 9 here, okay? All right, or I could correct this and say standard deviation of x is sigma equal to 3. Okay. Any questions about the z-score? Many times we refer to the unit normal, that is a normal distribution whose mean is 0, with standard deviation 1, or n01, as the z distribution, or the unit normal distribution, okay? So let's go down here and play a different game here. Suppose that we're given the z-score for Jane's test score, and we're told that the test scores are normally distributed with a mean mu of 70 and a standard deviation of 12. So our test scores are distributed as n 70, 12. So we're given the mean and the standard deviation. We're told that her z-score was 2.2. In terms of absolute x's, is that a good score? All right, now again, the so-called empirical rule that I mentioned before tells me that 99% of the data in a normal distribution lies within 2 standard deviations of the mean. So if you go from -2 to 2, you capture about 99% of the data. So a z-score of 2.2 is really good. It's way out there in the right tail. So let's see what it becomes if we now apply our equation here for z-scores, and we'll calculate her absolute score on the scale. Okay, so we have an equation here, z-score on the left, is the quotient of the difference of her score with the mean divided by the standard deviation of the distribution. So that gives us a simple linear equation which we can easily solve for x, right? So when we solve this equation for x, this is from your algebra class, right? And we get our value for x as 96.4. And that's a pretty good score, isn't it? Relative to the other scores in her class, her z-score of 2.2 is really high. In this particular example, where the test scores have a mean of 70 and a standard deviation of 12, her absolute value, her absolute score x, calculates out to 96.4. Okay. Any questions about number 2 there? Calculate your x score based upon your z-score, considering that x is a normal distribution with mean 70 and standard deviation 12. Okay, let's go to the next problem here. And this is a problem where now we use our z-scores and measure up with different populations, okay? So this man, B. Zishan, was, let's see, in 2009, okay? His height was calculated to be 2.26 meters. Now remember that 1 meter is 39 inches. So he's got a height of over 7 feet, right? Okay. And so in 2009, the tallest woman in the world, M. Didek, measured at 2.18 meters. So in terms of these two populations, the men and the women's heights, who's taller? Okay. All right. So even though the man is taller here in relative term, in absolute terms, he's 2.26, she's 2.18. Let's see how they stack up within their populations. Okay. Now we're told that the male populations are normally distributed with a mean of 1.75 meters and a standard deviation of 0.15 meters. And then similarly, we're told that for the women's heights, they conform to a normal distribution with a mean of 1.62 meters with a standard deviation of 0.12. So the mean in the women's population is smaller, but the standard deviation is less. That comes into play, doesn't it? Because the standard deviation is the quotient in our z-score. So now we can say, okay, let's calculate z-scores. Compare those. When we take Zishan, his z-score is 3.4, right? Take his height, x, subtract the mean of the distribution of those population, that population, 1.75, divide by the standard deviation, and we come out with his z-score of 3.4. He's way, way out in the right tail. He's the tallest man in the world, right? Now, when we do this for the Didek score, Didek height, and we get a ratio of 4.6. So clearly her z-score is higher. So we might call her the tallest person in the world. because we've measured z-scores for these different populations, and she comes out with the highest z-score. All right? So this is how we might use z-scores to compare two populations. Any questions about number 3? Calculating your z-scores. Okay. All right, so now let's move down to numbers 4 and 5 here. And we're given a variable, or a continuous variable x, which represents the overhead reach distance. And we're going to try and design a workstation such that it's comfortable for the user of the workstation in terms of reach, overhead reach. So we're given the distribution of the overhead reach in terms of centimeters. We're told that the overhead reach for adult females is a normally distributed random variable whose mean is 202.5 and whose standard deviation sigma is 8 centimeters. Okay. All right, so there's our data. And now we're going to answer the following question. Let's randomly select a female, measure her overhead reach, okay? And then we'll find the probability that it's between 194.5 centimeters and 210. These might be the specs that the manufacturer is offering. Now, he wants to make sure that the probability of the distribution, all right, is high for those values. If it's low, it may not be a good design, right? Okay, so we'll go to StatCrunch. We'll go to the normal calculator in StatCrunch. We've already been to the calculator in StatCrunch for the binomial distribution, all right? And that occurred in worksheet 5, right? So if we go down the list, in our calculator list, under stat, we find the normal distribution, don't we? Okay. And now we can use that function to calculate the area under this PDF, this normal probability density function that was given to us up here. And we can calculate the probability. Remember, area under this probability density function represents probability. So the two limits that were given up here in number 1 are 194.5. Here are the limits here. And the right limit is 210.5. And if we use StatCrunch, the area between these two limits is given to us to be about 68%, 0.68. All right? So go into StatCrunch, go to your stat super function, and set up your problem in StatCrunch the way I've done here, and it'll come back with this graph showing you the shaded area, which represents the probability, and it'll calculate the probability for you. Okay. Now, let's look at this value down here, 68%. Is that good enough for the manufacturer to go ahead and build the workstation according to those specifications? Well, I don't know. It might be a little low. We might want to capture more probability. So he might want to design his workstation so that its mean that the distribution either has a smaller mean or the standard deviation is smaller. There's less dispersion. Okay, that's how we can adjust these probabilities, either by adjusting the mean or adjusting the standard deviation. Okay, all right. So this gives you basically this is like a histogram, isn't it? It shows you the relative frequency on the Y scale, which is probability density, and then it shows you the scores on the x-axis here. So it's showing you how the data using this model is distributed. And we can extract probabilities based on this model. Okay. Okay, so there we get the probability, all right, using StatCrunch. Now your textbook also has tables in the appendix. And before we had StatCrunch, students used the tables, okay? But my recommendation is don't use the table. It's a little more tedious. It's more prone to error. If you go into your StatCrunch package, your StatCrunch spreadsheet, go to Stat, go to Calculators, go to Normal, fill in your data box as specified in StatCrunch, and then you can calculate your probability using StatCrunch. Okay, so I'm hoping that you're doing it that way for your homework and your worksheets. Okay, let's do the last one now. Any questions about number 4?
Yes, Professor. Why is the standard deviation 8?
Because it's given to you in the model. We're told that these overhead reach distances are normally distributed with a mean of mu, and this other value in here in the shorthand notation represents the standard deviation. Remember what I mentioned up here in the instructions. The instructions show you that this notation, x twiddle n mu sigma, tells you that x has a normal distribution with mean mu and standard deviation sigma. So now you look in your problem and you say, haha, he's telling me that my mean for x is 202.5. Look at this graph down here, and you can see that the center point of this distribution is right at 202.5. If you visualize a line of symmetry going right through the middle of this distribution, it'll be at 2.2.5. And then the variance, or the standard deviation, measures the dispersion, okay? All of these normal distributions have area 1. So as the variance increases, it'll flatten out the distribution. You'll get more dispersion away from the mean. That's what this picture is telling us. Okay, this one doesn't look too bad. It looks like it has a pretty tight dispersion. The standard deviation is 8 centimeters. Okay, that's where the 8 comes from. See that? Okay, we're told that the model is a distribution whose parameters are mean, mu, 202.5, and standard deviation 8. And that's what you'll use in StatCrunch to get this curve, which then gives you the probability, or the area that's shaded in red here. And that area is about 68%. Okay. Does that answer the question?
Yes, thank you, Professor.
Okay, good. All right, let's go to the last one here now. Now, this last one embodies a very special wrinkle. In number 4, we talked about a single observation called X, or little x. But in this last problem, what we're going to do is take a sample of size n. All of these samples, x1, x2, all the way up to xn, they're all drawn from the same distribution, okay? But under the so-called central limit theorem, the variance of this sample mean, remember the sample mean is the sum of the x's divided by n. That's the sample mean. Now, that has a different distribution than x. Why? Well, because of the central limit theorem. The difference in the distribution is that the variance of x bar is sigma divided by the square root of n. So by taking multiple observations and taking the sample mean, the theoretical standard deviation of x bar has a standard deviation which is inversely proportional to the square root of n. Again, if you had all the samples, that ratio basically would go to 0 and you would have everything concentrated at the mean. But of course, in any distribution, there's dispersion. There's differences in the values, right? Okay. So in order to calculate number 5, we have to be aware of that theory, which tells us that x bar is, yes, still a normal distribution, and yes, it has the same mean as x, but its standard deviation is sigma over the square root of n. So when we go into StatCrunch to calculate the probabilities for x bar, we have to proportion out sigma with the square root of n to get the correct answer. So let's do that in number 5. Okay, so in number 5, we're asked if 64 females are randomly selected, find the probability that they have a mean x bar overhead reach distance between 200.5 centimeters and 204.5 centimeters. Okay, so here's what we're calculating. There's our probability that the random variable x bar lies between 200.5 and 204.5. Okay, so now our random variable x given to us in problem 4 has a distribution normal mu sigma, where mu is 2.2.5 and sigma is 8. So by the central limit theorem, the distribution of the sample mean x bar has the same mean. That's called an unbiased estimator. So when the mean of x bar is equal to the mean of x, we call it unbiased. But the standard deviation, you must divide by the square root of n, or you'll get an incorrect answer when you measure probabilities of the sample mean x bar. Okay, so a single observation x is a lot different than an aggregation of n x's. So the distribution of x bar by the central limit theorem is sigma over the square root of n. So now what we have to do is calculate this new standard deviation. It's called the standard error, 8 over the square root of 64. We're told that n is 64, and since our central limit theorem tells us that the distribution of X bar has a standard deviation of sigma over the square root of n, we divide 8 by the square root of 64 and we get 1. So now we have a new distribution for X bar. Okay, does everybody follow that? Look at the difference between 4 and 5. In 4, we just had the one observation, and in 5, we have sample size n equals 64. We have to take that into account in order to get the correct probability. It's a fairly heavy type theoretical result. In applied statistics, we don't worry about the theory, we worry about the correct application of the theory. So to correctly apply this, we have to take sigma over the square root of n. We get a new distribution, and here it is. Okay. Now, when we go into StatCrunch, we use a standard deviation of 1, right? That's sigma over the square root of n, and same mean. X and X bar have the same mean, 202.5. Okay. All right. And here we get the area between 200.5 and 204.5. Okay. And here we get the probability of about 95%. Now remember that I told you at the beginning, the empirical rule tells us for normal distributions, within 2 standard deviations of the mean, you get about 95% of the data, right? And since the standard deviation of this distribution, X bar, is 1, 2 standard deviations would be 2. 202.5 plus 2 would be 204.5. 202.5 minus 2 would give us 200.5. So you see there's exactly about 95% distribution with probability within 2 standard deviations of the mean. So this verifies our empirical rule for this distribution. Okay. All right, any questions about any of these 5 problems? Study these problems, and if you put these under your belt, and if you're able to use StatCrunch to calculate these normal probabilities, you really have a tool. Okay, you have a great tool for applying theory, a fairly advanced theory, to elementary statistics. Powerful, very powerful what we've done here. Okay, so again, we're taking our data, we're modeling it using a normal distribution. Okay, and if we can assign parameters to that model, we really do have something going for us. Okay. Any other questions about worksheet 6? Is it good? Is it all clear? Okay. Okay, so there are lots of stuff going on here, right? You've got central limit theorem, you've got normal distributions, you've got StatCrunch. So there's a lot in here. And if you can, like I say, get it all squared away, you'll have really a great resource and a great understanding of elementary statistics here. Okay. Okay, do you guys want to go over worksheet 5 quickly? You've handed that in last week. I was out last week. I'm just now getting back. Okay. Yeas or nays on worksheet 5? I did post it for you in the announcements. Let's go back to your announcements here. Okay, so here you have the announcement that I posted last night with all of the solutions of worksheet 5. So you should look at that. I'll be correcting your worksheets as well and giving you some feedback with that. Okay? Questions, comments? Let me go ahead and check the chats here. Okay. I've got some questions about StatCrunch. Okay. Let me just give you a very quick. Okay. The question was, how do I calculate a normal probability in StatCrunch? I believe that was the question. So as I mentioned in your worksheet, take your stat super function up there in StatCrunch. You get this list and take the top of the list, which is your calculators list. That pops up. Move over to your calculators list. Okay, some of you have used the binomial. I saw that in earlier worksheets. So let's go down. This is listed in alphabetical order. And this is a pretty complete list of distributions, continuous and discrete distributions in elementary statistics. Let's go down to the normal. Click on the normal distribution. Okay. And here it presents you with a Z distribution, a unit normal, meaning that the mean is 0 and the standard deviation is 1. That's what our textbook is calling a Z distribution or a unit normal distribution. And now we're going to go to work. We can change the mean, right? So this function allows us to cook up a wide variety of calculations for various normal distributions. Back in our worksheet here, remember what I did there. Let's see, I had in number 4, we had a mean of 202.5. And we were given a standard deviation of 8 for those overhead reach distances, right? This is in problem 4. And then we were asked to calculate the probability between 194.5 and 210.5. So let's choose the button up here that says between. Okay. And now we can select our left and right limits. So let's type in our left limit there. We're calculating the probability between 194.5 and 210.5. And we'll hit compute now. And there you see, you get your 68%. Okay. Don't use your table in Triola. You can. Actually, it'll strengthen your skills in statistics, all right? But it's not necessary to do it that way. You can do it right here in StatCrunch. All right, let's set that one aside and do the other one, okay? So we'll do this. We'll, in number 5, okay, you all see what I did there? It goes really fast, doesn't it? I chose stat. I chose the top option here, calculators. Then I went over to the right and went down the list until I grabbed the normal. Okay. It displays, its default display is a unit normal or a z-normal. So now I'm going to give it the parameters for number 5, same mean as number 4. However, the standard deviation is not 8 as it was over here, right? Central limit theorem tells us it's sigma over the square root of n. So that makes 8 over the square root of 64, and that gives us 1. So we're good to go there. Now we choose, whoops. We choose between, and our limits are 200.5 and the upper limit was 204.5. And now hit compute, and that gives us the correct answer of about 95%. Okay, and then you can see that this one here, I think this would be a good exercise for you to see that since the standard deviation is smaller on the right, remember we've divided by the standard error, sigma over the square root of n, so that makes the standard deviation of this distribution smaller. It means it's more concentrated about the mean. And if you gaze at these scales, you can see that that's true, right? Okay, so that's a very quick overview of the worksheet. Hopefully there's enough detail there for you so that you can go in there and do it on your own. Now, starting with worksheet number 7, I will be requiring you to submit your homework, your worksheet, using StatCrunch. And no scans anymore. I'll enunciate that policy in an announcement. So you will no longer be able to download your worksheet, print it out, fill it in with pencil and ruler. You'll have to download it as a word processor document, Google Docs, Microsoft Word, whichever one you want, and then copy and paste your results from StatCrunch into your word processor document, and then attach both your word processor document, .pdf, .docx, whatever it is, along with your .scs StatCrunch session. And remember, we went over that, I believe, where you were able to use your StatCrunch super function over here, download your results, and then go ahead and upload that file in Canvas so that when I grade your worksheet, you'll be able to go ahead and just upload it. No scanning required, okay? Is everybody clear with that policy? No more paper copy, paper, pencil and ruler. Some of you have already been doing this already. I get some very nice documents where you've cut and pasted all your results right from StatCrunch. What I didn't get from you before, because I didn't require it, was your session. But now I'm going to require everybody to go ahead and attach their .scs file. I'll open that up and I'll clearly see in StatCrunch how you've done it. Okay? Okay, guys, any questions?
Yeah, I actually have one. So just to make sure, I'm guessing you would like us to still copy and paste all the graphs onto the actual worksheet itself and then also do the .scs file?
Yes.
Okay.
Yes, you'll have, just like I showed you, let's see. Just like I showed you in this, oh, I'm sorry, I had it right there and I missed it. Yeah, so what you'll submit to Canvas is something that looks exactly like what I showed you here.
Mm-hmm.
And then in Canvas, you'll have all of your graphics showing here, and you'll have the .scs. Now, I'm not requiring it with this one. Some of you have already submitted it. It's due tomorrow night. But in the next group of worksheets that you get, you'll be required to copy and paste all your results from StatCrunch. And in addition, you'll also have your .scs, okay?
Gotcha.
Now, some of you are thinking, well, wouldn't it be cool if I could just give him a .scs file and it's got all the worksheet material in it along with the results? We haven't gotten to that step yet, but that could happen down the line where you don't even have to use the word processor. You can just use StatCrunch here. Okay, where's the StatCrunch? It's in here somewhere. I've got to move this guy here. There it is. Okay, and you could actually create a very nice worksheet document right in StatCrunch. You can just type your results right in here and then have your results listed. Okay, here's all your results. And that's the Express, right? Some of you are looking at it that way and saying, wait, that really makes a lot of sense. But in the meantime, until I change we'll go step by step here. And until I change the protocol on how you submit these, we'll go with this. Okay? Let me see, where did I? Okay, any last questions here before we sign off? Did I cover all the chats? I think I did. Okay. All right, guys. Let's go Padres. I know some of you are Padres fans are out there like me. We got a good team. I think we can go deep in the playoffs. All right, see you guys probably next week. I'll make an announcement as to whether we'll have a session on Thursday.
Are you going to have office hours today, Professor?
At 11:30?
Yes. Okay.
Yes, I'll come back on at 11:30 for our office hours, okay?
Okay, thank you.
Okay, guys. See ya. Bye now.
Thank
Go Pods.